In this video, I will show you how to find the vertical asymptotes and holes of rational functions. This is AP Pre-Calculus, topics 1.9 and 1.10. If you appreciate this content, please show it by hitting that like button. A hole occurs when the factor in the denominator cancels out with the factors in the numerator. A vertical asymptote occurs when a factor in the denominator cannot cancel out with factors in the numerator. Look at this example. F of x will have a hole at x equals 1 because the factor in the denominator cancels out with the factor in the numerator. We will also have a hole in g of x, still at x equals 1. Even though we have two factors of x minus 1, they will both be canceled out with the factors in the numerator. There'll be one factor of x minus 1 left over in the numerator, but that doesn't matter. All of the denominator factors canceled out, so that's going to be a hole. We get a vertical asymptote when we have a factor in the denominator that does not cancel out. So you see the x minus 1 in the denominator, and it does not cancel out with anything in the numerator. So we will have a vertical asymptote at x equals 1. Now, in g of x, we still have a vertical asymptote. Even though this factor of x minus 1 cancels out one of the factors of x minus 1, it's still not a hole. It's going to be a vertical asymptote because we have this leftover factor of x minus 1 in the denominator that does not get canceled out. In summary, when you are looking for holes and vertical asymptotes, in both cases you are looking at the denominator. It will be a hole if the denominator gets canceled out. It will be a vertical asymptote if the denominator does not get canceled out. Notice that this graph has a hole at x equals 1. I want to teach you about this limit notation when you see a negative sign as a superscript. This would be read the limit as x approaches 1 from the left of f of x. So this describes what happens to the y values as we approach 1 from the left. So notice as we get closer and closer to an x value of 1, we get closer and closer to a y value of 3. So that's why we say the limit as x approaches 1 from the left of f of x is 3. When you have a hole, it's going to be the same limit from the left and from the right. As we approach an x value of 1 from the left, notice that again we are approaching a y value of 3. So we would say the limit as x approaches 1 from the right of f of x is 3. This graph has a vertical asymptote at x equals 1. Let's consider the limit as x approaches 1 from the left. It would be like this. As we get closer and closer to an x value of 1 from the left, the y values, or the value of f of x, just keeps falling. It decreases without bound. So the limit as x approaches 1 from the left of f of x is negative infinity. Now let's consider the limit as x approaches 1 from the right. As x approaches 1 from the right, f of x increases without bound. So we say the limit as x approaches 1 from the right of f of x is positive infinity. Example 1. For each function below, determine the x values of any holes or vertical asymptotes. For both cases, we are focusing on the denominator of the rational function. If a factor in the denominator cancels out completely, then that gives us a hole. If it doesn't, then it gives us a vertical asymptote. So I see this factor of x plus 3 in the denominator, but this factor cancels out completely with another factor in the numerator. So this tells us that we have a hole at x equals negative 3. The x minus 5 does not cancel out. So this tells us that we have a vertical asymptote at x equals 5. Part B. To be clear, x minus 2 squared means x minus 2 times x minus 2. So I think I'm going to write it out so you can see more clearly what's happening. Similarly, x plus 1 squared means x plus 1 times x plus 1. We are hunting for vertical asymptotes and wholes. We study the denominator. Any factor in the denominator will either give us a vertical asymptote or a whole. If it cancels out completely, it's a whole. If it doesn't, it's a vertical asymptote. So let's start with x minus 2. X minus 2 does cancel out with one of these factors of x minus 2. So as far as the denominator goes, it's completely gone. That means this is going to give us a whole at x equals 2. Now, what about the x plus 1? This factor of x plus 1 does cancel out with another factor of x plus 1 in the numerator. However, we still have an existing factor of x plus 1, so it did not completely cancel out. This will not be a whole. This will be a vertical asymptote at x equals negative 1. So if it doesn't cancel out completely, it's a vertical asymptote. Part C, let's factor the denominator. I see a common factor of x, so let's bring that out. That leaves behind x squared plus 4. Be careful, the difference of two squares, like for example x squared minus 4, factors x plus 2 times x minus 2. But the sum of two squares is unfactorable. So do not make the mistake of trying to factor this as x plus 2 times x plus 2 or something like that. It's unfactorable. So that means we will not have any wholes because neither of these factors will cancel out. However, we will have a vertical asymptote at x equals 0 because of this x. Will I get any asymptotes from the x squared plus 4? No, I won't. That's because if I set x plus 4 equal to 0 and solve, I'm going to get imaginary numbers. So this would be x squared is equal to negative 4. Taking the square root of both sides, this will give me x is equal to plus or minus 2i. Imaginary zeros are not vertical asymptotes. They don't show up on the graph at all. Another way to think about it, what values of x would cause the expression x squared plus 4 to equal 0? Well, there aren't any. Remember, if you plug in a negative number, it's going to become positive. So no matter what, this term is going to be positive. The smallest this term could be would be 0. But 0 plus 4 is still bigger than 0. So there's no possible way that x squared plus 4 will equal 0. Thus, no additional vertical asymptotes. Example 2. Write a left and right limit statement as x approaches 2 for each of the following functions. The key is to decide whether there is a whole or a vertical asymptote at x equals 2. If it's a whole, the limit from the left and right will be the same constant, and that constant will simply be the y value of the whole. If there's a vertical asymptote at x equals 2, the limit from the left and right will be positive and negative infinity, and I can show you how to decide whether it's positive infinity or negative infinity. Look at part A. Will we have a whole at x equals 2 or a vertical asymptote at x equals 2? It'll be a whole if the x minus 2 cancels out. If it doesn't, it's a vertical asymptote. It's going to be a vertical asymptote at x equals 2 because the x minus 2 does not cancel out with anything. Since we have a vertical asymptote at x equals 2, the limit from the left or right will either be positive or negative infinity. It's just a matter of how do we know whether they are positive infinity or negative infinity? All we have to do is to decide whether each of these three factors are positive or negative, near to, but a little bit to the left. The two factors in the numerator are easy, because the sign near to will be exactly the same as the sign at 2. So just plug in 2 right here, and that'll tell you the sign near to. This would be 2 minus 1, which is positive 1. So near to, this factor is positive. Near to this factor is also positive because 2 plus 3 is 5, positive 5. So near to this factor is positive. The only one that takes a little bit of thought is the x minus 2 itself. We can't just plug in 2 because that would just be 0. That's where the but left part comes in. So think of a number that's a little bit to the left of 2. It would be best to think of a number like, 1.9 or something like that. If I do 1.9 minus 2, is that going to be positive or negative? That's going to be negative. If the 1.9 hurts your brain at all, it would actually work fine if you pick kind of any number to the left of 2. So, picture 2 on a number line. You could actually just use the number 1 if it makes you feel better. If you plug in a 1 right here, you would get 1 minus 2. That's negative 1. So, to the left of 2, you're going to get a negative. So, to the left of 2, is the overall sign of f of x positive or negative? Well, if we have an odd number of negatives, it'll be negative. An even number of negatives means it'll be positive. We just have the one negative. So f of x will be negative a little bit to the left of 2. In other words, the limit as x approaches 2 from the left of f of x is negative infinity. How about a little bit to the right of 2? Well, these two factors in the numerator are not going to change because near 2 we're still just plugging into positive, positive, just like before. So the only one we have to worry about is the denominator. A little bit to the right of 2, this factor will be positive, because now we're talking about things like 2.1. So 2.1 minus 2 would be positive. Or again, if you don't like the decimals, if this is 2, to the right of 2 on the number line would be 3. You could just use 3 if it makes you feel better. 3 minus 2 is 1, that's going to be positive. Clearly, the overall sign of f of x will be positive in this situation. In other words, the limit as x approaches 2 from the right of f of x is positive infinity. Part B. First, ask yourself, do we have a vertical asymptote or a hole at x equals 2? Since the factor x minus 2 cancels out completely, we will have a hole at x equals 2, not a vertical asymptote. As a function approaches a hole from the left or from the right, the value of the function is not approaching positive or negative infinity, it's approaching a constant, the same constant from the left and the right. And that constant will simply be the y value of that hole. We know the x value of the hole is 2. To get the y value, simply plug the x value into the function, or at least what's left of it after you cancel out the x minus 2. So if we plug in 2 here and here, we're going to get 2 plus 4, which is 6, and then 2 minus 3, which is negative 1. So that y value is negative 6. And that is the limit from the left and the limit from the right. Part C. Do we have a hole or a vertical asymptote at x equals 2? We have to be very careful because we have x minus 2 squared. You have to remember that that means x minus 2 times another x minus 2. I don't have room over here, so I'm going to cross out the exponent and write the second x minus 2 separately so you can really sort of see what's going on. So if the x minus 2 in the denominator cancels out completely, then it's a whole. If there's an x minus 2 left, then it's a vertical asymptote. You can probably tell what's about to happen. The x minus 2 in the denominator cancels out the x minus 2 in the numerator, but we had 2 of them in the denominator, so there's still one left. Because there is a surviving x minus 2, that means h of x has a vertical asymptote at x equals 2, not a whole. Because we have a vertical asymptote at x equals 2, the limit from the left and the limit from the right will either be positive or negative infinity. To figure out whether it's positive or negative infinity, we need to figure out whether these remaining factors are positive or negative near 2, but a little bit to the left. So near 2, the x minus 4 is going to be negative, because we can actually just go ahead and plug the 2 in, and that would be 2 minus 4, which would be negative 2. So near 2, this factor is definitely going to be negative. In the denominator, the x minus 1, we can again just plug in the 2. 2 minus 1 is 1. That's positive. So near 2, x minus 1 is positive. We can't just plug in the 2 for x minus 2, because that would just give us 0. So this is the one where we have to say, but to the left, a little bit to the left. So instead of 2, you could think 1.9. 1.9 minus 2 is going to be negative. Overall, h of x will be positive because of the even number of negatives. So the limit as x approaches 2 from the left of h of x is positive infinity. Okay, how about near 2 but to the right? This is the only one we have to change. X minus 2 is negative to the left of 2, but positive to the right. For example, if x is 2.1, 2.1 minus 2 is positive. Or even if x is, let's say 3, that's to the right, 3 minus 2 is positive. The overall sign of h of x in this case will be negative, because we have an odd number of negatives. In other words, the limit as x approaches 2 from the right of h of x is negative infinity. Example 3. Write an equation of a rational function with the following limit properties. Looking at part A, notice that the limit as x approaches 3 from the left and the limit as x approaches 3 from the right both equal a constant. That means that there is a whole at x equals 3. Also, this constant is the y value of the whole. So the whole is at x equals 3, comma, y equals 5. Let's begin to build our expression for f of x. We know that we get a whole when a factor cancels out completely. To get a whole at x equals 3, we need a factor of x minus 3 in the numerator and the denominator, so they will cancel out. We need to create a function that will have a y value of 5 when x equals 3, after canceling out the x minus 3, of course. In order to make that happen, we will need to choose a constant very carefully. And right now, I don't know what that constant is. So I'm just going to put a C for constant, and we'll figure out what it is later. Now focus on the fact that the limit as x approaches 1 from the left and the limit as x approaches 1 from the right is some kind of infinity in both cases. That means we have a vertical asymptote at x equals 1. We know that a vertical asymptote comes from a factor in the denominator that does not cancel out. So we must have a factor of x minus 1 in the denominator, so we get this vertical asymptote. So this is basically what the function is. We just need to figure out what c is. Consider the related equation y equals c over x minus 1. This is the equation we would get after canceling out the x minus 3's. In other words, this is the same as f of x, but without the whole. The y value at x equals 3 will be the y value of the whole. We know that at x equals 3, the value of y is 5. So if we plug in 3 for x right here, y should be 5. In other words, and I'm going to switch this around, if I have c over 3 minus 1, that should equal 5. When x is 3, y is 5. But the only unknown in this equation is now c. So we can figure out what the value of c is very easily. 3 minus 1 is 2, so this is c over 2 is equal to 5, and multiplying both sides by 2, we get c is equal to 10. All we have to do is plug this back in for c, and kabam, that'll be the answer. So this is the answer to part A. Wait, erase that box for a second. I forgot one thing. We need to make sure that specifically the limit as x approaches 1 from the left of f of x is negative infinity, and the limit as x approaches 1 from the right of f of x is positive infinity. First, let's check the limit as x approaches 1 from the left. So near 1 but left. The x minus 3's are going to cancel out, so they will not factor into our analysis right now. 10 is positive at the moment. If we need to change it, we can. So all we need to worry about is the x minus 1. We can't just plug in 1 because that would be 0. So what about to the left of 1? Well, this factor will be negative to the left of 1. For example, if I put in 0, that's to the left of 1, I would get 0 minus 1, which would be negative. So that would make the overall sign here be negative. It would be 10 divided by a negative number. So that means the limit as x approaches 1 from the left of f of x is negative infinity, which is what we wanted. Now let's check the limit as x approaches 1 from the right. So near 1, but to the right. To the right of 1, x minus 1 will be positive. For example, if I plug in 2, 2 minus 1 is positive, which makes this positive. So the limit as x approaches 1 from the right of f of x is positive infinity, which is what we wanted. So the answer was correct as is. If the signs had been backwards, I could have just changed the 10 to a negative 10, and that would fix the problem. Part B, the fact that the limit as x approaches negative 2 from the left and from the right both equal the same constant means that we have a whole at x equals negative 2. The constant tells us that the y value of the whole is 4. Let's start building our expression for f of x. A whole at x equals negative 2 means we need to have a factor that cancels out in the numerator and the denominator. So I'm going to put an x plus 2 here and here. We need the y value to turn out to be 4 whenever x equals negative 2, after canceling out the whole, of course. To make that happen, I'm going to need a specific constant right here. But I don't know what that is yet, so I'm going to call it c. Notice that the limit as x approaches negative 1 from the left of f of x and the limit as x approaches negative 1 from the right of f of x are both infinity. When that happens, that means we have a vertical asymptote. So we have a vertical asymptote at x equals 1. That means we have a factor in the denominator of x plus 1 that does not cancel out with anything. There's something different about these infinities compared to the last problem. When you look back at part A, notice that we have negative infinity and positive infinity. They're different. But then here on part B, we get positive infinity from the left and from the right. That's a little bit strange. Think about the sign of f of x near negative 1. We can ignore the x plus 2's because they are just going to cancel out anyway. So we're just left with the c and the x plus 1. We can make the c whatever we need it to be. For right now, let's imagine that this is a positive number. The factor of x plus 1 is 0 right at negative 1. It'll be negative to the left and positive to the right. So assuming that c is a positive number, to the left we would have negative infinity, and to the right we would have positive infinity. That's no good because we want positive infinity both times. It will not help to change the value of c to a negative number, because then on the left we'd have a negative divided by a negative, and that would be a positive. But then on the right we would have a positive and a negative, that would be a negative. So we're still going to get one negative and one positive. The problem is that x plus 1 changes signs. It's negative on the left and positive on the right. How do we stop that from happening? To stop this factor from changing signs to the left and to the right of negative 1, we could square it. This way it'll be positive either way. Now let's find the value of c using the related equation y equals c over x plus 1 squared. This is just f of x after you cancel out the x plus 2's. In other words, after you remove the whole. Let's evaluate this equation at x equals negative 2. Because at x equals negative 2, we know the y value will be 4. So if we plug in negative 2 for x, so that's negative 2 plus 1 squared, we should get 4 for the result. So this is going to give us c over negative 2 plus 1 is negative 1. Negative 1 squared is positive 1. So c over 1 is equal to 4. In other words, c is equal to 4. Substituting 4 in for c, we get this expression for f of x. Think about the sign of f of x as x approaches negative 1 from the left and from the right. We would cancel out the x plus 2's. 4 is positive, so that just leaves the x plus 1 squared. Because this is squared, it's going to be positive from the left and from the right of 1. So everything's going to be positive no matter what. Positive infinity on both sides. So this is the answer. Example 4. Sketch a picture of a rational function that has the following properties. Part A. F of x has a whole at x equals 1. I'll come back to that. As x approaches 4 from the left, f of x increases without bound. As x approaches 4 from the right, f of x decreases without bound. So that sounds like a vertical asymptote at x equals 4. Let's go ahead and draw that. Something like this would satisfy the last two criteria. As x approaches 4 from the left, f of x increases without bound. As x approaches 4 from the right, f of x decreases without bound. All I need is a whole at x equals 1. So this is one graph that would work for part A. Your answer will look a little bit different than mine. That's okay. Part B. G of x has wholes at x equals negative 2 and x equals 3. I'll come back to that. As x approaches negative 1 from the left, g of x decreases without bound. As x approaches negative 1 from the right, g of x also decreases without bound. That sounds like a vertical asymptote at x equals negative 1. Let's draw that. As x approaches negative 1 from the left, f of x decreases without bound. And as x approaches negative 1 from the right, f of x decreases without bound. I keep saying f of x. It's g of x. So all I need is a whole at x equals negative 2 and a whole at x equals 3. So let me work that in. So this is one example of a graph that would satisfy all criteria. There are many. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.